Moving data between registers and memory is one of the most fundamental operations we can do in software development. So naturally, our next task should be the implementation of various different move instructions. Let's start by visualizing all the different encodings and parameter combinations in one handy table. There are way too many variations here, so let's throw out anything we don't want to consider right now. All we really need for the foreseeable future is the ability to move data between memory addresses and registers, so any encodings that operate on segment offsets are irrelevant right now. We're also going to stick to 32 and 64-bit data for now, so we can remove anything operating on 8 or 16 bits. Finally, there is no actual instruction for moving 64-bit data to a memory location directly. We can only move sign-extended 32-bit data to 64-bit addresses. We're not going to bother with the specifics of dealing with something like that, and will instead use two moves to replace it for now. Now that we've cleaned up our scope, let's get to know the instruction itself. The move instruction takes two parameters, the source and the destination. When executed, it does exactly what the name already implies: move data from the source to the destination. If we want to use 64-bit parameters, we'll need to add the rex prefix we encoded in an earlier video. This is then followed by one of 4 different opcodes which each corresponds to a different set of parameter types. So for example, if we want to move data from a memory location to a register, we'll need to use the opcode 8b. A key detail we'll need to consider for our implementation is that when we want to move an immediate value into a register, that destination is encoded into the opcode itself. For such an operation, the basic opcode is B8, to which we'll then need to add the register number. So for instance, if we're moving something to the EDX register, we'd need to add 2 to the number encoded by B8. The remainder of the encoding is just the parameters themselves. Most cases will require a mod RM byte for registers and a SIB byte plus displacement for memory addresses. Immediate data is then just appended at the end. As I started working on the implementation for this video, I noticed that the nodes we built in the last devlog weren't really usable in their current state. The main change I had to make was that we now actually do just have a single type for each kind of parameter, simply because it's much more convenient for actual use cases. Our memory address implementation was overhauled the most out of all, since the mode we encoded into different types now is part of the actual output data. Some other additions were made to that node as well, but there just is no time for that in this video. Luckily, our new community Discord gives you the chance to follow along with such developments much more easily. We recently started a small community project to build some basic documentation for all the nodes we're implementing on this channel. So if you also want to get access to my node file format early, head on over there via the link in the description below. While you're down there, feel free to subscribe if you haven't already. There's a lot of work to be done, and we'll eventually need all hands on deck for this and many other projects. The node we are going to build today will work just like the actual assembly instruction in traditional programming. It has 2 input sockets for the various types of data and an output socket that provides us with the encoded x64 instruction. So let's take a look inside. If you have no idea what you're looking at, I recommend checking out previous videos first. Especially my videos on compiler basics should help you understand the vast majority of concepts used here. Like every node graph, we start by defining the input ports. If we think back to the theory we just covered, we know that our source parameter can be a memory address, a register, or an immediate value. So let's connect some type nodes with the corresponding type strings to the source port. The destination of a move operation is almost identical to the source, it just can't be an immediate value. As I've already mentioned, I had to rework the 3 different data types we implemented in the last video. Part of that overhaul was the creation of what I'm calling receiver nodes. These nodes essentially take in a specific type of data we defined in another node and then split it up into its different components. So for example, our memory address data is split up into the 3 bits we need for a rex prefix, the 2 different fields we need for the mod RM byte, and so on. These receivers basically compress a lot of repetitive work down into single nodes, so we don't make an already complicated node graph even worse. Our first task is the construction of a rex prefix, since our parameters may be 64 bits in size. Since the parameter sizes of the move instruction are always identical, we only need to detect if the source operand is 64 bits large. Our receiver nodes provide truth values regarding the size of their input, so all we need to do is plug those into a pair of condition nodes. If either a 64-bit immediate value, a 64-bit register, or a 64-bit memory address is received, this second condition node will return true. We can then just plug that into the first of the 4 rex prefix fields. The next bit in the prefix is set to the additional bit of the destination register if one is provided. The procedure for the remaining 2 bits is identical to the first. We simply check if the SIP byte of a memory address uses a 64-bit register and set the bit accordingly. We then need to make this rex prefix optional, since it's only needed if we're moving 64-bit data. So we plug it into a value node, which is only activated if 64-bit data is actually used. This is technically not 100% correct, since there are other cases where the prefix needs to exist, but for our usage right now it will suffice. Next up is determining the correct opcode for the final instruction. To achieve this, we first need to determine which parameters are present. We can do this by simply checking if each input is an empty string or not. These booleans are then paired up into different AND operations representing the different parameter configurations we're expecting. We'll map the case of 2 register parameters to the same opcode needed for moving memory into a register. So we combine those 2 conditions with an OR operation here. We then simply map each of these conditions to value nodes containing the relevant opcode in hex notation. Only one of these conditions will evaluate to true at any given point in time, so only one of these value nodes will be activated. One of the final components to our move instruction is the mod RM byte. It will be needed for all variations in our encoding except when we're moving an immediate value into a register. So let's start by determining the correct pair of bits for our mode field. We get these bits from memory address inputs, if any are available. So let's collect them with this node. If no memory addresses are provided, we want to resort to the direct register mode. This collect node always outputs the last value it receives, so if we provide the direct register bits in the first slot, it will be overwritten if a memory address is provided. We then simply plug in this collect node into our mod RM constructor node. To determine the reg field of our mod RM byte, we simply collect the encodings of our register inputs. The ordering here is important because if we receive 2 registers, we want the source register to be stored here, not the destination. To achieve this, the source register encoding needs to be plugged into this collect node after the destination register encoding. We then need to employ a similar ordering scheme to determine the RM bits as well. The first slot is occupied by the destination register, the second and third by the source and destination memory addresses respectively. If we want to move the value at a memory location into a destination register, the destination register will be written into the reg bits and the RM bits. But since the collect node always outputs the last non-empty value it receives, the RM bits holding the destination register will be overwritten by the source memory address data. All that's left to do now is simply append any SIB, displacement, or immediate bytes we receive from a memory address input. Let's first collect the SIB and displacement bytes from the memory address receivers, convert them into text and append them to our instruction. If no memory addresses are provided to this node, nothing is added to the final encoding. To handle an immediate value, we could simply push them to the end of our instruction bytes. However, I'd like to provide some additional security to help avoid invalid encodings. As mentioned in the beginning of this video, it isn't possible to move actual 64-bit immediates into 64-bit memory locations. Right now, that is still a possibility with this node network, so what I'd like to do is automatically truncate any immediate values if the destination is a memory address. Let's first define the condition that will cause a truncation of the immediate value input. We then define 2 values holding indices where we want to split the byte string at, based on the condition. If we want to truncate, the immediate bytes need to be split at index 8, which would convert a 64-bit input into 2 32-bit values, while leaving 32-bit values unchanged. We activate these split indices based on the condition node, so only one is active at any given time. This allows us to safely add the values to converge the data streams into one socket. We then provide the raw immediate value to a split node together with the split index we just determined. The left sequence output of that split node then holds our truncated immediate value, which we simply append to our final instruction bytes. We then provide our instruction encoding to an output port, and with that have finished implementing the MOV assembly instruction. This resulting node can now be used just like the traditional assembly equivalent, hiding the complexity of the underlying machine code behind a much more understandable visualization. We're now one step closer to building our first Hello World program. One of the final pieces we are missing right now is a basic string data type. Subscribe to the channel to not miss out, and I'll see you there.